In this video, we are going to state several theorems about convergent sequences. The first result we have here is 6 statements that I like to call algebraic limit laws. So this tells us how to do algebra on the limits of sequences. So suppose here that C is a real number, just a number, and you have 2 convergent sequences. Suppose the sequence AN converges to the real number A, and the sequence BN converges to the real number B. It's important here that both of these sequences converge to numbers. What we have here would not work if either diverged or the limit did not exist. These are really statements about convergent sequences. So these results give us ways to combine convergent sequences, possibly to form a new sequence. So for example, if you formed a new sequence by taking the AN terms and adding them to the BN terms, the limit of this new sequence, AN plus BN, would exist, and it equals A plus B. Not very surprising. So you could read that as the limit of the sum is the sum of the limits. Similarly, if we take AN and we multiply every single term by the same number C, the limit of C times AN exists, and it equals C times A. The third result could really be gotten as a combination of the first two, but it's worth stating on its own. So the limit of AN minus BN is A minus B. You can see how that agrees with the first two lines. So the limit of the difference is the difference of the limits. Similarly, the limit of the product is the product of the limits. So AN times BN tends to the real number A times B. The limit of the quotient is the quotient of the limits. So if AN goes to A and BN goes to B, we can say that the limit is A over B, provided that B is not 0. So if BN is tending to either a positive number or a negative number, then the ratio AN divided by BN tends to A over B as n goes to infinity. Then we can take a convergent sequence like AN and exponentiate it. If we thought of this as AN squared, that actually falls under this line, but you could also look at this and think, hey, that's giving me the ability to do things like take square roots, because the square root of AN is like AN to the 1/2 power. So our final limit law tells us that AN raised to the P converges to the number A to the P, where here you want the AN to be positive so that you could do things like take square roots. The next theorem is a useful result called the Squeeze Theorem. Suppose that we would like to analyze the sequence Bn, and we know the behavior of two other sequences, An and Cn. It so happens that An is less than or equal to Bn is less than or equal to Cn for all indices n. Then if An and Cn tend to the same limit, the limit as n goes to infinity for both of these sequences is the real number L, then Bn has to also go to L because it's being squeezed between these two sequences. So if they're tending to L, Bn has to tend to L as well. Let's look at a classic example of using the squeeze theorem on this sequence, which is sine of n over n. Whenever you see trig functions in the numerator of this kind of quotient, you want to remember that sine and cosine values are bounded between -1 and 1. So I would start this by saying -1 is less than or equal to the sine of n is less than or equal to 1. This is true for any angle that you plug into the sine function, including 1, 2, 3, 4, 5, 6, 7. So this is always true. Then what we can do is divide all three terms by this denominator n. So now we have our original sequence, sine of n divided by n, squeezed between two other sequences whose behavior we already know. So in the language of the theorem, -1 over n is the an sequence. The middle one, sine of n over n, is the bn sequence whose limit we're trying to take. And then the one on the right is cn. Now we know that 1 over n tends to 0 as n goes to infinity, so cn tends to 0. You could even use limit laws to justify that -1 over n would tend to -1 times 0 as n goes to infinity. So we know that an also goes to 0. Since bn has to be sitting between these two sequences and they're both going to 0, the limit as n goes to infinity of sine of n over n exists and equals the number 0. Let's visualize this example. So what I would like to plot for you are three functions first. So this first one is the function y equals 1 over x for all positive values x. That's this hyperbola in the first quadrant. Then this hyperbola down in the fourth quadrant, this is the function y equals -1 over x for all positive x values. And then squeezed between them or sandwiched between them is this sine of x over x wave. You can see the oscillations, the fact that we go down and then up and then down and then up. That's from the sine of x part. But because we're dividing by a denominator, which is getting larger and larger, the amplitudes are getting smaller and smaller. So that's why that function sine of x over x looks like that. We can see it's being squeezed between these two hyperbola. This is just a picture of the functions. We could add to it the graphs of these sequences for the first several sequence terms. So in particular, this first dot here, this is the term sine of 1 over 1, then sine of 2 over 2, sine of 3 over 3, sine of 4 over 4. And if we remove the functions, I think it makes it harder to see. But here we have the sequence terms on the top of 1 over n, the negative 1 over n, and then we can see that sine of n over n is being squeezed between them. So since the top and bottom are going to 0 as n goes to infinity, sine of n over n is being sandwiched to 0 as well. So this is a nice application of the squeeze theorem. I would like to state 4 results about sequential convergence for you. The first one is a famous result called the Monotone Convergence theorem. This tells us that every bounded monotone sequence of real numbers converges. Monotone, recall, means that the sequence is either increasing or decreasing. Bounded means it's trapped. If you were to graph it, it would be trapped between two horizontal asymptotes. So how I like to picture this is if you have a roof and your monotone increasing, you have to level off. You have to tend to something. Or if you have a floor and your monotone decreasing, you've got to level off and tend to a limit. So this is a well-known result called the monotone convergence theorem. Then our second result is stated a little strangely here, but let me explain what it's trying to say. If we have a sequence of numbers converging to a limit L, then if I were to extract a subsequence, say of the form the even terms only. So this first notation here is saying, look at the even subscripts and form what's called a subsequence out of those. So I'm going to take every other term, A2, A4, A6, A8. This sequence, viewed as a sequence in its own right, also converges to L. Similarly, if I form a subsequence out of the odd terms, so take the first one, the third one, the fifth one, and form an infinite sequence out of those terms as a sequence in its own right, this subsequence also converges to the number L. In fact, this statement is true about any subsequence of this originally convergent sequence. So if you take an infinite list of numbers and you extract certain terms, preserving order, so that what you're extracting also forms a sequence, it also becomes its own infinite list of numbers, then any such subsequence would also have to converge to the number L. So if you're looking at terms and you're like, hey, every fifth term behaves a little differently, then maybe that's a sign that the sequence doesn't converge. Okay, the next result says that if a sequence converges, then it is bounded. So if a sequence is not bounded, then it cannot converge. All convergent sequences must be bounded. And then the final result says that if a sequence converges to L, where maybe the original sequence was all negative or mixed negative and positive terms, if you form a new sequence by taking the absolute value of all of your original terms, then that sequence also converges, and it converges to the absolute value of the original limit. Let's wrap up this lesson with a specific sequence, the sequence r to the n, for different choices of r. So we're looking at a sequence of the form r squared, r cubed, r to the fourth power. R here is the common ratio between those adjacent terms. And what we're interested in is for what choices of r would this sequence converge and what would it converge to? Because this lesson is one of looking at theorems, what I would like to do is answer this question by using the theorems that we've seen. So what I've done is broken this exercise into several pieces. The first thing we're going to do is use algebraic limit laws to figure out what the possible choices for the limit are. So could this converge to 20? Could it converge to -5? We'll figure out what the possible limits are. So when it converges, what could it converge to? Then we will manually show that it converges when r is 1, It's no surprise. If you just plug in r equals 1, you'll get the sequence 1, 1, 1, 1, 1. Okay, we've basically done it out loud, but I'll write it down. And it diverges when r is negative 1. Then we will prove that if the absolute value of r is bigger than 1, the sequence cannot converge. So it diverges whenever the absolute value of r is bigger than 1. However, it converges when r is between negative 1 and 1. If you put all this together, you'll see that the conclusion is that the sequence r to the n converges when negative 1 is less than r is less than or equal to 1. Let's answer the first question. If the sequence r to the n converges, what could it possibly converge to? And again, I would like to try to use our theorems to analyze this question. So let me write out what the sequence looks like. We have r to the n, which is going to look like r squared, r cubed, r to the fourth, r to the fifth, and on and on. What could be the limit of this sequence? So let's imagine that the sequence converged, and then we'll try to figure out what it could have converged to. Suppose that for some given value of r to the n converges to the real number L. So here L is a finite real number. Well, by one of our previous theorems, the one about subsequences, if we look at the subsequence of even terms, so the second term, the fourth term, the sixth term, that subsequence would also converge to L. So we could say the sequence that looks like r squared, r to the fourth, r to the sixth, r to the eighth, this subsequence would converge to the same real number. That was one of our previous theorems. Since these are terms that look like r being raised to 2 times something, so r to the 2 times 1, r to the 2 times 2, we can denote this as r to the 2n. So then the subsequence r to the 2n, r squared, r to the fourth, r to the sixth, also converges to L. However, there's a little trick here, and that is to notice that r to the 2n can be written as r to the n squared. So we can do exponent laws there to take that as r to the n squared. Since r to the 2n equals r to the n squared, and now by algebraic limit laws, we're saying that we have a convergent sequence being exponentiated to the second power. So this was actually the last limit law on the original opening slide, that if we took a convergent sequence and exponentiated it, it tended to the limit raised to that power. So r to the 2n also has to converge to the number L squared. In order not to be contradicting ourselves, that means that L must be equal to L squared. This gives us a condition on the limit L, and this is what allows us to know what the possible limits are. If L equals L squared, there are 2 possibilities, either L equals 0 or L equals 1. Those are the only possible limits for the sequence r to the n if it is to converge. For our next exercise, let's just look at 2 specific choices of r. If r equals 1, then r to the n is 1 to the n. For all possible indices n, and that's obviously just the number 1. So what we're looking at here is the constant sequence 1, 1, 1, which tends to the number 1. That agrees with one of our choices for a limit. So that checks out. What if r is negative 1? Then r to the n is negative 1 to the n, which is an alternating sequence. So when n equals 1, it's negative 1, then positive 1, negative 1, positive 1. -1, +1. I don't think you need too much convincing that this diverges, but what you could do if you wanted to use the theorems that we've seen is say, hey, look, the odd terms. So if I extract the subsequence of odd terms, that subsequence is converging to -L, or sorry, -1, whereas the even terms are converging to 1. If you reread that subsequence statement, we said that they both have to go to the same limit if a sequence converges. So the fact that these don't agree means that this diverges. Or you could just say the obvious thing, this is an alternating sequence of -1, 1, -1. This diverges. Okay, so we're done with this. Let's look at two more results, and I'm going to do these fairly rigorously. So I'm going to prove that r to the n cannot converge if the absolute value of r is greater than 1. And then we will prove that it does converge. In fact, it converges to 0 if r is between -1 and 1. For this first result, let me first verify that the absolute value of r to the n is an increasing sequence. Okay, so here we can say if the absolute value of r is greater than 1, multiply both sides by the absolute value of r to the n. So then the absolute value of r times the absolute value of r to the n is greater than 1 times the absolute value of r to the n. But if we rewrite this in a more natural way, the left side is absolute value of r to the n plus 1. And then the right-hand side is just the absolute value of r to the n. That means if I look at the absolute value of r to the n as a sequence, it's an increasing sequence. It's monotone increasing. If I consider the subsequence of even powers, then I can get rid of the absolute values because raising absolute value of r to an even power is going to make it positive without the absolute value. Okay, so consider r squared, r to the fourth, r to the sixth. Then what we can say is that for any such term here, it's greater than or equal to the previous term, which is greater than or equal to the previous term. All of these terms are greater than or equal to the size of r. So I just wanted to get rid of the absolute values, so I'm switching to this sequence. This is greater than or equal to the first term in the subsequence, which is greater than the absolute value of r, which is greater than 1. So we cannot force these terms to be as close to 1 as we like, which was our definition of sequential convergence. So in order to say that a sequence converges, you have to say that there's some threshold index beyond which all of the terms in the sequence are an acceptable distance away from the limit. And here we're saying that these are always larger than something larger than 1. So there's no way they can converge to 1. Likewise, they cannot converge to 0. So this sequence of even powers I just cannot write this. I'm trying to write r to the 2n. Diverges. But if that sequence diverges, then that means that r to the n would have to diverge. If r is greater than 1 or less than -1, this would be the subsequence of every other term where the index is even. Since it's not converging, the original sequence couldn't converge. Okay, this was perhaps a wordy way of saying that the sequence grows without bound to infinity. It cannot converge. So if the size of r is greater than 1, you cannot converge. R to the n cannot converge. Okay, let's talk about what would happen if the size of r was less than 1, or in other words, r was between -1 and 1. What I'm going to do is consider the absolute value of r. Let's consider the sequence formed by taking the absolute value of r and raising that to n. Since the absolute value of r is less than 1, following the same step I did here, so I'm not going to write it out in all this detail, we can say that the absolute value of r to the n plus 1 is less than the absolute value of r to the n. Therefore, this is a monotone decreasing sequence. But since we're looking at the absolute value of r, all of these numbers are between 0 and 1. So this sequence is also bounded. We have a monotone decreasing sequence which is bounded. So by the monotone convergence theorem, we know it converges. Kind of similar argument to what I did here. We are monotone decreasing away from 1. So we're less than 1, and then we're decreasing from there. So the limit is 0. Let me just say it goes to 0. I know it goes to 0 because that was the only other option for the limit of the sequence. Okay, now I'm going to knock out r to the n using the absolute value of r to the n and the squeeze theorem. Since -1 times the absolute value of r to the n is less than or equal to r to the n is less than or equal to the absolute value of r to the n, we just showed that the right side goes to 0. The left side also has to go to -1 times 0, so 0. The middle goes to 0 by the squeeze theorem. Okay, so let me give you a chance to think about that, and then I will summarize this result. Okay, now that we worked through all these steps where I was trying to use the theorems that we've seen as much as possible, let's summarize the result that we found. If r equals 1, then the sequence r to the n is the constant sequence of all 1s. This converges to the number 1. If r is between -1 and 1, then this sequence converges to 0. Otherwise, it diverges. Okay, so that wraps up that exercise. I wanted to look in detail at this sequence because we have a number being raised to consecutive powers here, and that's the kind of expression that we see a lot in sequences and series, so I thought it was worth taking a deep dive into the sequence.